Section: Introduction. In this section, we discuss how large language models have evolved to handle long contexts. Many models now support context windows ranging from 32K to 2M tokens, enabling them to tackle tasks like long document question answering, multi-document summarization, and code understanding at a repo level. One approach involves using alibi and rope embedding to train transformers on short sequences and then apply them to longer ones during inference. Other methods have pushed the boundaries further, allowing models to handle up to 2M tokens in a context window. Researchers have also explored techniques like context window sliding and segmentation to address the limited context window in original transformers. Innovations in model architecture, such as transitioning to recurrent or state space models from traditional transformer designs, have shown promise in improving long-range computations. These advancements have been integrated into various open-source large language models to enhance their understanding of long sequences. Evaluation of these long context models typically involves language model perplexity over long documents, passkey retrieval tasks, and long document question answering or summarization. While these evaluations set a baseline for model performance, they may not fully capture the model's ability to handle realistic long sequence tasks. For instance, in question answering, models may rely on shortcuts by reading only a snippet to predict the answer, rather than understanding the entire document. To address these limitations, we propose in context learning, ICL, on extreme label classification tasks as a more comprehensive evaluation method for long context language models. Unlike previous tasks, ICL requires models to scan the entire input to understand the label space, testing their ability to comprehend the entire sequence for making predictions. We have created a benchmark called LongICLBench, comprising 6 tasks of varying difficulty levels in terms of context length and label space, to systematically assess the performance of 13 long context models. Our analysis reveals that as tasks become more complex, the performance of models tends to decrease, with some models showing a linear degradation with increasing input length. However, within a certain range, most models benefit from extensive demonstrations. The distribution of label positions in the input significantly impacts the performance of models like GPT-4 Turbo in long in-context learning tasks. In summary, our contributions include the development of LongICLBench for evaluating long in-context learning tasks and assessing recent long context language models. By uncovering the sensitivity of these models to instance position in the prompt, we aim to provide insights for enhancing the design of large language models tailored for long context understanding. Section Summary. In this section, we delve into the advancements in large language models, LLMs, that have transitioned into the long context era, supporting context windows ranging from 32K to 2M tokens. Various techniques, such as alibi and rope embedding, have enabled training transformers with short sequences for inference on longer sequences. Evaluations of these long context models primarily focus on language model perplexity, passkey retrieval, and long document question answering, with recent research emphasizing in-context learning tasks to assess LLM's ability to comprehend and reason over entire input sequences. Section: Related work. In this section, we will discuss the related work on long in-context learning with large language models, LLMs. As pre-trained language models become larger, in-context learning, ICL, has become a popular method for handling various tasks without extensive fine-tuning. Research has shown that having more example demonstrations can improve ICL performance. However, some studies suggest that longer input prompts may reduce performance, as the effectiveness of large language models is limited by the maximum sequence length they were trained on. To address this limitation, different techniques like memory augmentation and extrapolation have been introduced to support ICL with a wide range of demonstrations. The effectiveness of transformer-based models is affected by the increase in computational cost as the sequence length grows, especially when dealing with long context inputs. Various strategies have been explored to tackle this challenge. Some studies focus on further fine-tuning the LLM with longer context inputs to adapt it to extended sequences. Others use techniques like position extrapolation and interpolation, based on relative rotary positional embedding, to extend input length beyond the training phase. Additionally, methods such as sliding memory window and chunk segmentation have been proposed to address computational issues. Alternative architectures beyond the transformer, like selective state spaces models, have also been investigated to handle long inputs more effectively. To evaluate the performance of long-range LLMs, several benchmarks have been developed. These benchmarks include tasks with sequences of different lengths to test variations of fast transformers. They cover a wide range of tasks with long context inputs to assess the capabilities of LLMs. However, none of these benchmarks specifically focus on exploring the ability of LLMs in long and context learning with extreme label space. Therefore, a new benchmark called LongICLBench has been proposed to provide a more comprehensive evaluation for LLMs in handling long context inputs efficiently. Extreme label classification involves categorizing data into a vast number of labels and is used in various real-world applications like emotion classification, named entity recognition, and biological function prediction. Existing methods for extreme label classification tasks range from embedding-based approaches to fine-tuned retrievals, focusing on managing and utilizing the large label space effectively. Integrating extreme label classification tasks with long context LLMs presents unique challenges due to the extensive label space, requiring precise differentiation among labels based on context. The proposed LongICLBench offers a range of difficulty levels to evaluate the capability of long context LLMs in handling extreme label classification tasks effectively. To evaluate long in context learning on extreme label classification tasks across different domains and difficulty levels, we have collected 6 datasets with varying context lengths. Each dataset contains a subset of classes to create evaluation sets with different rounds, where each round includes examples with unique chosen labels. The datasets include examples from different domains like banking intent detection, relation extraction from news and web text, dialogue-based relation extraction, and discourse marker identification. These datasets aim to provide a balanced evaluation of long in context learning for LLMs. Section Summary. In this section, we explore the challenges and strategies related to long in context learning on large language models, LLMs. We discuss how increasing the number of example demonstrations can enhance in context learning performance, while longer input prompts may diminish it. Various techniques like memory augmentation and extrapolation have been introduced to address these challenges and support in context learning with extensive demonstrations. Additionally, we delve into the evaluation of long in context learning on extreme label classification tasks, highlighting the importance of datasets with varying context lengths and difficulty levels to assess the capabilities of LLMs in handling such tasks effectively. Section: Model and Experimental Setup. In this section, we explored in context learning for extreme label classification. We evaluated various open-source long-context language models with around 7 billion parameters, including state-of-the-art models like Gemini and GPT-4 Turbo. Our analysis, as shown in the Models Overview table, highlighted different strategies used by these models to handle long contexts. Some models extend the training context window size, while others support length extrapolation. 2 new RNN-like architectures, RWKV and Mamba, were introduced to reduce attention complexity, enabling the models to handle longer inputs more efficiently. To ensure a fair evaluation, we created prompts based on a template for each dataset and sampled the same example set for all models with evenly distributed labels. We also tested 500 examples from each dataset, maintaining an even distribution of label types. Open-source models were loaded from Hugging Face weights, while API-based models were called using official scripts. Our experimental results, presented in multiple tables, showed that transformer-based models generally outperformed RNN-based models across all datasets. However, API-based models, especially GPT-4 Turbo, still outperformed both types. For simpler tasks like Banking 77, models benefited from longer contexts with more examples, leading to significant accuracy improvements. In more complex tasks like TAC-RED and Dialogue-RE, requiring better long context comprehension, all models' performance dropped compared to Banking 77. We observed that most models reached their peak performance around a context length of 20K, except for GPT-4 Turbo, which consistently improved with more demonstrations. In the challenging discovery dataset with 174 classes, even GPT-4 Turbo struggled to differentiate between fine-grained types, resulting in a score of 0. Our analysis across different datasets revealed models' varying capabilities in understanding different tasks. Inspired by the "lost in the middle" phenomenon, we conducted experiments to investigate whether the position distribution of instances affects performance in long and context learning for extreme label classification tasks. In our scattered distribution experiments on TAC-RED, we observed varying performances across models, with some showing consistent accuracy regardless of instance positions, while others performed well across a wide range of labels. Notably, GPT-4 Turbo consistently achieved over 80% accuracy for most label types. Section Summary. In this section, we conduct a thorough evaluation of various long context language models, including state-of-the-art models like Gemini and GPT-4 Turbo, to explore in-context learning for extreme label classification. We observe that transformer-based models generally outperform RNN-based ones, but API-based models, especially GPT-4 Turbo, excel. Additionally, our experiments reveal that the position distribution of instances within prompts can impact the performance of models in extreme label classification tasks, with some models showing consistent accuracy across labels while others perform better on specific labels regardless of their position. Section: Grouped Distribution. In this section, we compare scattered and grouped distributions by arranging instances of the same class together in the demonstration prompts. We then analyze how this organization affects model performance before and after grouping. The results are summarized in a table, showing a general decrease in performance for most models after grouping instances by class. Some models, like Mistral 7B-v0.2 base and Intern LM2-7B base, experience significant performance drops, indicating a strong sensitivity to instance grouping. To investigate further, we visualize the accuracy of grouped labels based on their positions within the prompt. The visualization demonstrates that instances of the same class are clustered closely together. We observe that certain models, such as Intern LM2-7B base, are highly sensitive to the distribution of instances and only perform well with labels positioned at the end of the prompt. On the other hand, open-source models like ChatGLM 3-6B32K show more resilience to changes in instance positioning, maintaining high performance across different positions with only a modest 3.3% drop in accuracy. Even the GPT-4 Turbo model is affected by group distributions, experiencing a significant 20.3% decrease in performance. This decline is consistent across models and is not influenced by the specific positions of the labels within the prompt.